Hey, good morning. Same morning. Awesome. Okay, so I was just looking at the stuff that we were, I have to make videos over, and I'm just so glad we're starting to get into this part of the year or this unit, you know, done drawing and getting into more math stuff. I really enjoy that. So, yay. There in unit 3, I got really tired of making videos and I was having a really hard time. I was like, I don't want to make that video, but these I find more fun. Okay, so net ionic equations. You just should have looked through solubility and electrolytes. So now we're going to relate that to net ionic equations. Okay, so let me share my screen and hopefully this goes well. Sometimes it's better than others. My throat does hurt though. Okay, so let's see. We probably will just jump right on in here because there's not much explaining to do. Let's write a complete chemical equation. All right. Actually, shoot, I'm sorry. What is a net ionic equation? Net ionic equations. They are good, okay? They are, sometimes you get asked on AP, like, why do you use net ionic equation? It's literally a question. Why is a net ionic equation good to use for this? Why? Because it shows the actual reaction. The actual reaction that is occurring and removes spectator ions, right? Excuse me. It removes what we call spectator ions. Okay, so that we can see the actual reaction, what's really occurring. It makes it easier to visualize what's actually occurring, okay? So let's go. Basically, only rule, guys, if aqueous, sorry, and 100% soluble. What do I mean by that? Not a weak acid. That's all I mean. And once we cover like acid-base equilibrium a long ways from now, you'll understand what I mean by that. But if aqueous, then dissociate. And for hopefully, most of your examples will not have weak acids right now. Okay. What is a strong acid? Just for those of you overachievers, the strong acids are HNO3, HClO4, H2SO4, we'll put a star by him, HCl, HBr, HI. There might be one more. Sometimes people say HClO3. But if it's not weak, if it's not strong, it's weak. But these are strong. Strong means 100% dissociation. Okay? So if it's not a strong acid, it's a weak acid. Don't worry too much about that right now, please. I'm sorry, I probably shouldn't have even said it. Let's give an example here. All right, so let's say that we've got, I have to think in my head here. Let's say that magnesium, oops, that does not say magnesium. I'm thinking in my head. Magnesium nitrate, aqueous, all right, reacts with, what's going to be? I need to make sure, I'm trying to get a precipitate in my head. So let's make that sodium phosphate, aqueous, all right? So let's go ahead and just write that reaction and turn it into our net ionic equation. MgNO3 2, aqueous, that's magnesium nitrate, reacts with sodium phosphate in A3PO4, aqueous, to produce magnesium. Oh, magnesium phosphate, Mg3PO4 2. That is going to be my precipitate, guys. He's not going to be it's not going to dissolve. And sodium nitrate. And I can already see that I'm going to have 6 of this. And this is group 1A, always soluble, also nitrate, also always soluble. Therefore, this is like MeJo soluble. Let's look to make sure this is balanced. I've got 2 phosphates, 2, 3, 3. All right. So there is my balanced chemical equation. But our topic here is net ionic equations. So let's first write our complete ionic equation. And while we prepare to do this on your AP and AP Chem, on your exam, and on lots of the quizzes that you will have coming up, where you like free response quizzes, you will want to make all of your equations net ionic equations. You will want to make all of your equations net ionic equations. So I'm just going to leave it at that. All right, complete ionic equation. What am I going to do? I'm going to dissociate all aqueous ionic compounds. That's what I'm going to do. I'm going to dissociate all my aqueous ionic compounds. All right, I just thought about something I should have said. I'll bring that up later. Okay, so this is ionic and it is dissolved. So I'm going to have 3 magnesium ions floating around in this solution. What that means is I don't have magnesium nitrate in the solution. I have the ions in the solution. So I'm going to show that. I'm going to have 3 magnesium ions. I'm going to have a total of 6 nitrate ions floating around in my solution. This is a dissolved ionic compound, so let's dissociate it into 6 sodium ions floating around the solution, and we will have 2 phosphate ions floating around in the solution. All right? Okay. I'm going to come to our arrow, and we say that this is a solid. So it's not dissociated. It is a solid. It is a precipitate, right? This is your precipitate. Okay? This is your precipitate. It is a solid. It thus remains as a solid. And then we get over here, and I see that this is aqueous. So I'm going to separate it into its ions. Okay, so right now I have a complete, little bit messy, ionic equation. If I've stated this before, I'm going to go ahead and take this chance or this opportunity to state it again. If you do not put these charges, and that's a bad color because it covers them up. If you do not put these charges here on your ions, you have done it's incorrect. We're communicating. This is a way of communicating. And if you leave the ions off, you're communicating incorrectly because they're ions, okay? So all we need to do now is cross off what we call our spectator ions. What do spectators do? Spectators sit and watch. They do not participate. Well, it looks to me like nitrate rather was a spectator, 6 and 6. Sodium was a spectator, 6 and 6. And what I'm left with are is actually what formed my precipitate. I've got 3 magnesium ions reacted with or located a phosphate ion and formed the precipitate magnesium phosphate. And that would be a solid in my solution that I could allow to settle, or I could, what are those things that go around real fast? I can't think of it right now. I lost it. Somebody will tell me in class, go around real fast. Okay, it'll come to me. Okay, so what I have here is a formation of a solid right? I've got reactions that occurred in solution, right? I had two solutions mixed together and I formed a solid. The formation of the solid could be called the driving force of this reaction, okay? Because if we had not formed this solid, think about it logically, if we had not formed this solid, then what would we have had? We would have had magnesium ions, right? And we would have had the phosphate ions, and we would have been able to cross those off as well. And we would have been left with absolutely nothing left over. And we would not have had a reaction. We would just had a bunch of ions floating around together, right? They're all spectators. They're all just chilling out. We just have a lot of ions in there. So the fact that we formed this solid caused those ions to not cancel out, right? So that we were in fact left over with something that actually occurred. So that was the formation of the precipitate, and that could be said to be the driving force of this reaction. Okay, all right. Now let's look at another example of a different driving force, and now we will have our driving force being the formation of water. And the easiest example to give of that is just to give a strong acid and a strong base. Go ahead and be aware that the presence of that hydroxide makes this basic. We're going to get HOH or H2O. That is a liquid. It is pure, a pure liquid, and sodium chloride, which has a group 1A and dissolves. So I would turn that into a complete ionic equation by separating strong acid. He separates. Anything with a group 1A is soluble, and we see that here. So what we really have floating around the solution is this here. Now, a pure liquid, that does not dissociate. That is a pure liquid, water, right? Only aqueous dissociates. Sodium chloride is dissolved, so we will dissociate him. And guys, I shouldn't say him, but I always do. Let's go ahead and get rid of our spectator ions, the ions that are the same on both sides of the equation, chlorides, sodiums, and let's look at what we're left with. Hydrogen bound hydroxide to form liquid water. So our net ionic, what we are really concerned with, what shows us what actually happened in the solution was that each hydrogen ion found a hydroxide ion. They formed a chemical bond or bonds, right? Covalent bonds actually, and formed water, liquid water. So this is not ionic, right? It's not ionic, but the ions do come together to make this molecule that is sharing electrons. There's not really ionic, okay? But that's how it's different. So water's cool like that. So the formation of water here is the driving force, right? Right. This is the driving force, the formation of water. Okay. And then you may be thinking, well, what about, what if there's a gas, right? So we're going to have the driving force equal formation of gas. So what I'm telling you guys is when you have solutions, you can think of this as reactions in solutions. If you don't form a solid or a liquid or a gas, then you don't have a reaction. You don't have a driving force, okay? Formation of gas. All right. So that would be, I'm thinking in my head, what am I going to write? I'm going to get one of those carbonates and an acid that we talked about, right? Or maybe not an acid. Let's say that we've got we'll do the sodium. We've already done this equation, right? We're going to make that a solid this time. So I've got baking soda. I'm going to react it with acetic acid. Now this is not, I hope I don't make a mistake here. This is a weak acid. Sometimes this one, never mind, weak acid. And I'm going to mix those. And I'm going to end up with sodium acetate, which would be soluble due to the sodium. And remember, I'm going to get water and I'm going to get carbon dioxide gas. Well, you don't usually do net ionic equations for this, but we could. And let's just follow the rules. That's a solid, so it's really not in ionic form. Now you could, I mean, you know, once it gets into the water, I mean, and then the acetic acid is weak, so it's not completely separated either. It's not a strong electrolyte. It's not ionic. It's an acid. Acids are molecules, okay? And now we can separate, dissociate. It should scoot over. I'm going to run out of room and keep this together. Now we can dissociate the sodium and the acetate, right? The acetate ion. Water stays together, and our CO2 would also stay together. So we don't have a lot to get. I don't see anything, right? Remember when I said you wouldn't really write a net ionic equation for this, but this shows everything as it actually exists, right? And it doesn't really help that much, but you do see that we also do not separate our gas, okay? So not very relative to this reaction, but we have water as a driving force and the formation of the gas as the driving force. You could argue that this is going to dissociate as soon as you put it in here, and you're correct. And we don't need to worry about all that. Okay, I think we're good there. All right. All right. Okay. Let's go.